we start, I want to give some or provide some information about our workshop. So first, some information of our workshop, then you can find more information about our workshop on our website, and then provide some information about the structure of the workshop. So first of all, the topics of our workshop covers general proximity sensors and also multimodal sensors, different kind of robotic skins. And another topic is the bridging from tactile to proximity perception. We have bio-inspired robots, multimodal sensors for soft robotics, and various kind of applications. So if you have topics regarding, or if you're working in this field, maybe you can participate in the next workshops. So the workshop's goal is to continue foster the community. So the idea is to provide some insights in our current research and industry, and let experts from different kinds of research provide some experience or introduction to the technology. And we also want to provide a platform for PhD students to collaborate or exchange information and chat with the community. So historically, since this is the fourth workshop, there was, I think from last year, there was a PhD forum, or even earlier. It was always nice platform to have some kind of possibility to exchange information with colleagues. So if you want to stay in touch with us, you can subscribe to our email list or mailing list. We will provide some information when there are upcoming events. And if you want to support us, work for the organization team. If you think this is a cool idea, you want to organize and have your own ideas, you're welcome to join our team for future events. So don't hesitate to contact us. So now a short overview of our workshop. We have a panel discussion on the 27th of September, 2-hour live session at the IROS event. And right now what we are doing is recording the on-demand material with the PhD forum. So every PhD candidate has around 50 minutes to present their work, or ongoing work. And we have a little bit more time, for like 5 minutes to meet each other and chat. So let's start with the fourth workshop. We have today four talks, starting with Serkan Ergun, and then Rachael Burns and Abu Bakar Dawood. Then we have Escobedo and Matthew Strong. All right, so starting with the first presenter, Serkan Ergun. I'm happy to introduce Serkan, who is right now a PhD student at the University of Klagenfurt in Austria, where he also finished his master's in mechanical engineering with the title Uncertainty Modeling of Sensor Systems. And his current interests are in human-robot interaction in the context of safety, proximity, and tactile sensing, and mechanical design. He's also a good friend of mine, and we have worked together in the past for the last ICRA 2021. So thank you, Serkan, for contributing to the workshop. And you can now start your screen, if you like.
Thank you very much. I will just use this second to share my screen with you. So thank you for the introduction. Today I want to present you my ongoing work towards safe physical human-robot interaction with capacitive sensors for tactile and proximity perception. I would like to kick off this presentation with my motivation. And it begins with the first law of robotics presented to us by Sir Isaac Asimov, that a robot may not injure a human being or through inaction allow a human being to come to harm. So this is, of course, not a scientific postulate, but more science fiction. But even back then, this statement is more valid than ever. And also, I want to just introduce you the most important terms in this presentation. most of you will already know them, but for those who doesn't know them, this talk focuses about human-robot collaboration, which means that a human and a robot perform a certain task together, as opposed to human-robot coexistence, where they just simply are present at the same location at the same time, but do not perform a task together, like I said. More precisely, human-robot interaction is a combination of HRC and some sort of communication between a robot and the human, which can be a gesture, a voice, for instance, of the human being, and some sort of, again, audio or visual output of the robot. And physical HRI is then the actual physical contact between robots and humans. But the question is, now what is safe physical HRI? And safe is not really a term which is fixed, and everybody has different opinions on the word safety. In this manner, the European Union, for instance, has a clear definition on safety. For a lot of products, they have directives, for instance, also for machines, for which robots are also part of. And these are laws within the European Union. So if a manufacturer of a robot, for instance, wants to introduce his new robots into the European market, he needs to follow this machine directive. As laws are just very general and they do not give you any insights on anything, there are safety standards or technical specifications. And for robots and human-robot collaboration of some sort, there are some applicable standards which are shown here. For the industrial case, the ISO 10218, then most importantly, the ISO TS 15066, which focuses directly on collaborative robotics, but there are also some standards on personal care, the ISO 13842, and 2 standards on medicals. And as I already said, the ISO TS 15066 focuses on robots and robotic devices, collaborative robotics, and in there are 4 operation modes listed for human-robot collaboration, and one of them, namely the power and force limiting, allows physical contact during operation. And in that mode, only the force is limited and the power and force is limited by the robot itself and not by external sensors. So we can only monitor forces, or at least get into that once the contact has happened. This is where my research then more or less kicks in. So let us go into the physical interaction a bit more of definitions. So the contact, which we call physical interaction, can either be intended, which is then an actual interaction, or it can be unintended, which is considered as a collision. And there are 2 different cases also presented in the ISO TS 15066 for transient and quasi-static contacts. And transient contact, which means that there is a sudden impact, for instance, from the robot to the human being, which can be free, which allows the human being to bounce back, or a clamped collision, where a human being first is impacted by the robot, but is later on, for instance, clamped between a wall and the robot, or between 2 parts of the robot itself. And quasi-static contact is more or less the long-term situation, which is also more or less the clamped situation, where the human is trapped, or let's say a niche scenario is also the free case, where a human being is trapped but not forced in the position. So it can move freely, let's say, to a certain degree, at least the human can breathe, for instance. And the ISO TS 15066 additionally lists biomechanical limits for force and pressure for transient and quasi-static contacts. And it lists those for 29 different body areas. And with those, one can determine joint and actuator velocities which the robot may have prior contact. In my work, I also, of course, did a literature study in the beginning, and this is just some of the work which I have been investigated prior to my research. And I just wanted to show you there. And next up, I want to give an insight on the problems and the open research topics of my thesis. So robotic systems at the moment, considering human-robot collaboration, have a low performance because they only allow low operating speeds of the robot during PFL scenarios, which means that we need some sort of proximity sensors to detect human beings priorly to make the robot move faster and increase the performance of the robotic system. Additionally, open research topic is the contact and collision modeling. So we need a more accurate prediction of forces, as we only can measure the forces at the moment after the contact has happened at the robot. And in this time, if we can simulate those, we have time. We win time by doing experiments as they within time doing the simulation, as it's usually faster than do experiments physically. And most importantly is actually to combine both the proximity perception and to cover the modeling of physical contacts. And by stating these problems, I want to address now the research questions which I presented to myself in my thesis. The first one is how can the performance of physical human-robot interaction with respect to operating speeds and force monitoring be improved, and which type of sensors are suitable? Is there an adequate solution to model collisions between humans and robots using simulation software to reduce efforts in experiments? And how do these aspects differ between rigid and series elastic robotic solutions, and how do they differ for both stationary and mobile robots? And finally, what are the required steps towards a certifiable solution with respect to safety standards? From these research questions, I have defined some objectives of my thesis. And the first one is to create a model for physical HRI while ensuring power and force limitations. It should be applicable for intended interaction and unintended contact, such as collisions. And the simulation, and there should be a simulation of this physical human-robot contact. And whenever feasible, it should be solved analytically. These results from this simulation should be validated using real-life test scenarios under different conditions. Can be different robots, but also different environmental conditions. And whenever possible, all approaches shall be generalized to be applicable for most conditions whenever possible. Addressing the first research question on how the performance of physical human-robot interaction can be increased. As I stated earlier, we want to make the robot move faster, or in some PFL situations, we want to make the robot move at all. In some situations, it can be that the robot is not even allowed to move because he will never obey to the PFL limitations. So we need to detect the human being priorly. In this manner, we need to determine the allowed operating speeds, which we can obtain using such proximity sensors, and additionally observe the forces during contact. And there are various sensor solutions which can be used. I considered visual, optical, radar, ultrasonic, and capacitive sensors. I only considered here in the range for human-robot collaboration, as we all know that visual and radar and even ultrasonic sensors, optical sensors have much higher ranges, but we only consider the human-robot collaboration cases where usual work cells have typical dimensions of a couple of square meters. Visual sensors are very well developed, and we can also do tactile measurements with it already. And the downside is that visual sensors, for instance, are limited due to light conditions and may cause surveillance issues of the workers of the human-robot collaborating cells, which at least in Europe do not like to be observed by cameras. Optical sensors, on the other hand, have their own light source and are also very well developed. They have the downside, a little bit less downsides, just fog, dust, and rain, which they are also limited in usage. Radar sensors give us additionally velocity information, and we can also do classification with it. On the downside is that for high resolutions, we need high bandwidths, and this could also decrease our performance if we want a system which is fast. Ultrasonic sensors, on the other hand, they are cheap, accurate, and give a rather accurate distance, as we know from parking sensors for vehicles. On the other hand, their performance highly depends on the reflection characteristics of the object. Capacitive sensors, on the other hand, have a much lower range than all the other sensors presented here, but their advantage is that we can also do some tactile measurement with it and that we suffer from no blind spots. And for the case for PFL, where we want to monitor a human which is very, very close to the robot, because for other cases, we might use the other operation mode speed and separation monitoring, where the speed of the human is adjusted, let's say, to larger distances. Capacitive sensors fit quite suitable for very short ranges because they are very reliable and they produce our results very fast. So we can have very fast result if there is a human being in the proximity of the robot. Going further into details, I want to show you how we determined operation speeds during the research. And let's say the permissible operation speed of a robot determines on many, many different factors. One is, of course, the deacceleration capabilities of the robot, which I will go into detail a little bit later. The latencies TSTR of the sensor and the robot. And there's also a factor of the permissible contact speed, which is, for instance, given by the ISO TS 15066 for different body regions, and the safe detection distance, let's say a distance where an object is detected with high confidence within a certain range. And the deacceleration, which I talked about, is very complex and is a function of the robot's pose, its mass distribution, its braking capabilities, so its braking torque, as well as friction, gravity, centripetal, and Coriolis forces. And to determine all of those, we would need a whole bunch of experiments, which is in my thesis part of future research. And just to show you on how the different permissible robot speeds with the help of capacitive proximity sensors might improve the performance. You can see in this figure where I've shown you the operation speed of a robot prior to detection for different body regions. If you have a safe detection distance SS of 0, which means that you do not have any proximity sensors there, the speed is much lower for certain hostile body regions which allow low contact speeds. For body regions, for instance, which allow high contact speeds, such as the finger, I just see an error there because there is a little bit of error here. The green one should be the finger and not the knee. So please just flip the orange, and the green one was just a mistake from the previous presentation. So the orange one should be the finger, which allows high operating speeds. There is also the benefit of the sensor, not that much. And we consider, let's say, distances of 0 to 20 centimeters in our research, because there, for hostile body regions, we already have lots of impact. On this matter, we already published a paper together with Yitao Ding and Hossam Malaki and many others, a unified perception benchmark for capacitive proximity sensing towards safe human-robot collaboration. And in there, we focused on capacitive proximity sensors for perception of humans close to the robot between 0 and 20 centimeters. And we designed a unified test procedure where we resemble multiple human body parts by simplified test objects. For instance, a cylinder for fingers, a sphere for a fist or elbow and shoulder joints, and a ellipsoid, for instance, for hostile body regions such as the human face and the chest. And in there, we also defined a safe detection distance where we showed the potential increase of a robot speeds, allowing the robot to pursue tasks at PFL applications. Next up is the collision modeling and the research question if there is an adequate solution to model collisions between humans and robots using simulation software. And such a solution should handle rigid, elastic, and elastoplastic collisions. It should have an FEA solver. It should include multiple sensor simulation possibilities, and it should be capable of doing it real time. Two options came into my mind. One was the simulation open framework architecture, SOFA, which I also used in my research, which I'll show you a little bit later on, and FAMPEX, multi-threaded deformable physics. The collision handling, which is also currently a work in progress, as I already said, is done in SOFA. And let's say the collision is handled in a that way. For instance, you see the big cylinder here, the gray one, which you should think would be a robot link on which a capacitive sensor together with a deformable ring shown in green is mounted on. And then you have some objects. In this case, it's just a cube. And this cube is colliding with this deformable layer, changing the distance between the sensor electrodes and the object, which are then let's say two plates of an condensator. And they also, when such a deformable layer is put pressure against, it deforms and its atomic structure is condensed, and also the permittivity, for instance, of the ring will change, and we can measure forces with it. This is also current work in progress, and I hope that I can present some results in the near future on this. And finally, I would also address the last research question on how the aspects differ between rigid and series elastic robotic solutions, and how do they differ for stationary and mobile robots. Well, let us consider stationary robots, which we all know are these series robots, for instance, the UR10, which is also shown in the bottom corner, but we also have mobile robots, wheeled robots, which can be mounted with a gripper or with a robotic arm as well, or not. And then we have rigid, series, elastic, and soft robots, which also give us quite the differences. A collision with a human being and a rigid robot will make most of the collision energy absorbed by the human. Whereas for series elastic robots, the collision energy is split up between the robot and the human, as the robot is able to retract a little bit from the collision and absorb some of the energy as well. And of course, the amount then depends on the stiffness of the series elastic robot. And for soft robots, on the other hand, most of the collision energy is then absorbed by the robot itself. And also this topic is a part of my further investigations. And to end these presentations, I just want to show you some of the robots which are used in my work. And I would like to end this presentation here, and I'm now open for a fruitful discussion and your questions. Thank you very much.
Yes, thank you. Really nice work you're doing. Also, very nice that you're considering the safety specifications for collision avoidance or all the stuff. So you're considering the safety specifications inside your work, which is often not done. Just most of the work we are seeing is, hey, we can achieve better safety and all the stuff, but seeing it from this perspective is something refreshing and new. Thank you. Are there any questions from the audience? You can, if you have any questions, you can raise your hand. A virtual hand. Okay. No questions. Maybe I have questions regarding your the heavy robot you were referring, and the elastic collision between human and robot. How do you think it will compare to existing robots that have impedance controllers, for example?
So you mean the difference on the heavy robot with an impedance controlled robotics?
Yes.
I haven't worked much with impedance controlled robotics in the past, but one big advantage is that you can set this more or less pre-default by hardware, and you can really adjust the robot prior hand to make it really, really soft. So you can do not only, let's say, gravity compensation, but you can have the robot just to lift it with one finger in one direction. So it will be really soft, and you can adjust it to almost rigidity as well.
I mean, I'm not a mechanical engineer, so I don't really know how it works with regards to how well it will absorb forces. For example, an impedance controller or a robot with impedance controller is actually very stiff. It behaves only soft because of its torque sensing within its joints and reacting according to the sensor measurements. So do you think that the impedance or an actual mechanical flexible robot has better impact attenuation capabilities in terms compared to a virtually rendered soft robot?
I would say yes, because in the heavy robot, for instance, you can set the stiffness by hardware default. So it is set and this will always be there. And for instance, if you suffer from power shortage, the series elastic part will still stay. More or less, if the robot loses its power, it will just swoosh down because it has no actual brakes, and will no longer exert any kind of forces there as well.
Right. Yeah, thank you for your presentation again. And if there are no further questions, thank you for participating and contributing to our workshop. And we will switch to the next speaker, or I will introduce the next speaker. One moment. Right. So the next speaker is Rachael Burns. She's currently a PhD student at Max Planck Institute for Intelligent Systems. and she finished her bachelor's and master's in biomedical engineering from the George Washington University in Washington, D.C., USA, and her research area is human-robot interaction. And her research, where she is particularly interested in socially assistive robots for children with autism, which is a very interesting application, I think. So instead of going to the common research area, I think the social area is very refreshing area. So thank you, Rachel, for joining us today. We are very excited to hear about your current research. And I will hand over the control of your screen to you.
Awesome. Thank you very much. All right.
Okay, sure. Because I tried to book the lab, but it was full.
Okay.
Yeah, that's
I
the
will
thing.
try to
We
turn
couldn't,
off the audio.
it's really busy now.
Okay.
Awesome. Okay. Thank you very much. Oh, you know what? I'm realizing I need to share it with, oh, it was on. We are good to go and we'll get started. So I want to thank you all for the introduction. My name is Rachael Burns, and I'm a PhD student in the Max Planck Institute for Intelligent Systems. And today I want to tell you about my doctoral research, which focuses on ultimately teaching safe social touch interactions using a robot koala. So social touch is touch with both communication and emotional intents. For example, poking someone on the shoulder to get their attention, maybe rubbing someone's arm if they're sad, or offering someone a hug. These are all examples. But for children with autism, sometimes social touch can be a little difficult. They may be touch averse, so maybe they are uncomfortable with new touch sensations, or they don't like touching other people. Or on the opposite end, they may be very touch seeking. So they may use touch to explore the world. So they may touch things very often, or maybe accidentally touch in a way that's a little bit too rough. And so often these children with autism will work with an occupational therapist, and that's where they learn about safe and appropriate social touch interactions. And in the field of human-robot interaction, it's increasingly gaining interest, the idea of bringing robots as additional education tools into these therapy sessions. One of the problems, though, at the moment is that these robots have almost no touch perception. So if we have robots and add touch perception to them, that brings a whole new set of educational games and activities that these robots can assist in to help these children learn about touch. So my colleagues and I are investigating whether a robot with augmented tactile sensing can help children with autism learn about safe and appropriate touch. And the way that we're doing this, our robot prototype is Hera, or the haptic empathetic robot animal. And as you can see, Hera is actually a commercial now robot in a fuzzy koala suit. We've added a tactile perception system on top of the robot, which are a set of fabric tactile sensors and a gesture classification system. And Hera will use this tactile perception system to then identify how it's being touched and then react in a way that makes sense and helps the child learn using a customizable emotion response system. So this is our overarching goal, but to kind of take a step backwards and go back to the beginning. So we had this idea that adding touch perception could be useful for robot-assisted therapy, but we also wanted to know whether this idea would be something that the autism and autism support communities would want. And if so, what features, what touch perception features would be most important for this therapy robot to have? And so to study this, this is actually the first journal paper that my colleagues and I wrote about Hera, or the Hera project. We conducted interviews with 11 autism specialists. And by speaking with these specialists, these were people that worked with children with autism from many different occupations. We had occupational therapists, physical therapists, speech language pathologists, and they had lots of experience, many years of experience working with children with autism. We had some participants that had up to 30 years of experience. And so we were able to get really good feedback from them about what features could be used and could be generalized to this whole spectrum of what the children might need. And so for our interview study to start, we went through and drafted initial requirements. So what we thought children with autism would need their robot to be able to detect based on what we saw in the literature. So this was from reading about children with autism and also reading about human-robot interaction and any instances of physical interaction between the child and the robot. Next, we had a structured interview with each of the specialists. And in this interview, we asked them to comment on and rank these initial requirements. We asked them if there was anything they wanted to add or edit, or if there are any requirements that they thought were actually not very useful that they would recommend removing. And this interview was about 1 hour per person. So after we got all these interviews from these 11 specialists, we then analyzed what they had to say using thematic analysis. And so to do that, we first transcribed the interviews and then coded everything the therapist said line by line. And when we were coding, we were looking for details that particularly stood out, or things that we saw recurring throughout different specialists' interviews, or if we saw anything that contrasted between the specialists' opinions. And then we grouped these codes into themes. So we had overarching, most important takeaways that the specialists were recommending. So from these 3 resulting themes that we got, we were able to finalize and update those initial requirements we wrote. So we finalized a set of qualitative requirements that are kind of layperson's terms of what a touch perceiving robot needs. Then using our own engineering backgrounds, our knowledge about sensors, machine learning, human-robot interaction, and also looking into the literature for best practices, we were then able to translate these qualitative requirements into quantitative specifications. So that way, roboticists and engineers had a blueprint to directly implement into their own robot systems. So we came up with 7 key requirements, and there are qualitative descriptions and quantitative specifications for each of these. First off, the robot should be robust and able to withstand rough play from children. Secondly, the therapist asked that our sensing range should mimic that of a human's. So that way, what the child is learning in the therapy session can be directly related to their real world experiences. So the robot should detect the gentlest touches all the way up to like a hard squeeze when it becomes painful and not fun anymore. The therapist also asked us to consider the feel of the robot. If the robot is an unpleasant texture, the child might not even want to play with it. So they said to make it soft and pleasant, maybe squishy. In terms of gesture identification, the therapist pointed out that the thing that was most important to them is that the robot identify whether the touch was socially appropriate or socially inappropriate, rather than knowing exactly what touch happened. And for spatial details, the therapist wanted to know the general area that the robot had been touched, like the upper arm or the hand. They didn't think the robot needed to know exactly where on the hand it had been touched. They also wanted the option to control the timing of the robot's response, either an immediate response or adding a delay if needed. And finally, this system should be adaptable to different robots of different shapes and sizes. So once we had our touch perception guidelines, we needed to create a touch perception system that met those guidelines. So the work that I'll be showing now is currently under review. This is our 2nd journal paper about the HERA project. And so it's a bit of a sneak peek. And so I'd like to show you our fabric-based piezo-resistive tactile sensors that we created. As you can see, these sensors fit on existing robots. We have it fitted on the now across its arm, and it goes under the koala suit. These are easy to make and pleasant to touch, and they are robust. So the way these sensors work is they have 2 layers of highly conductive fabric on the outside layers, and a layer of low conductivity foam sandwiched in the middle. And as the user presses on the sensor, it's bringing the 2 highly conductive layers closer together. So this is decreasing the space between the 2 highly conductive layers, and it's also decreasing the distance between, excuse me, I said that already, but it's decreasing the resistance of the sensor. So we can look at how the user is interacting with the sensor by looking at the instantaneous resistance. I also want to point out the fabrication process. Normally, sensors are made flat and intended for a flat surface. But our robot is not flat. It has lots of curved surfaces. We found if we took a flat sensor and tried to apply it to a curved surface, it really degraded the sensing range we had. What we found is that the outside layers are being stretched to fit onto that curved surface, whereas the bottom layers might be getting scrunched up. And so this pulling and squishing effect is replicating someone already essentially touching the sensor. So you lose a lot of the sensing range. So how we solved it was instead, we took a surface, a curved surface that matched the curvature of our robot. And we instead fabricated our sensor on that curved surface. And as you can see in the picture, that means that the layers of the sensor that are closest to the robot base are smaller. And as you get further out and the sensor gets thicker, the layers are larger to compensate for that. So this removes the stretching and sensor degradation that we were seeing. And so these tactile sensors are combined with a gesture classification algorithm that we created. And these form Hera's tactile perception system. And so we wanted to test our system out, see how our fabric sensors performed, but we also wanted to see how people performed, how people perform different touches, how similar or different their touches are. We also wanted to tell if our sensor could identify forceful versus gentle touches, for example. That's important towards identifying if a touch is socially appropriate or socially inappropriate. So we ran an initial user study with 15 healthy adult participants. We put 4 sensors on the robot's arm, as you can see in this picture, 4 different locations. And we asked the participants to perform 5 different touch gestures at 2 force levels, forceful and energetic. And so I'd like to show you an example of the participants' data. So here we're looking at the blue line. This is touch on the robot's hand. So you can see this user, it just performed energetic stroking on the robot's hand. And if we compare the stroking touch signature to this hitting one, we can see the stroking had much more gentle releases, whereas hittings was much more abrupt. And finally, with energetic tickling, you can see it's almost a noisy looking appearance. So these different touches have very distinct touch signatures, and these may vary even between different people. So yeah, in this upcoming paper, hopefully it will be published soon, we talk about how our classification algorithm performs based on the data we collected from these 15 participants. Just to quickly summarize, it look good, it does look promising, and it can identify different force levels and different touch gestures. So our next steps for our tactile perception system are to keep making more of these sensors to finish covering the whole robot. We have sensors across the robot's arm, and now we need to cover the rest of the body so that Hera can detect touch no matter where the child touches it. We're also working on a sensor design database so that we can share these sensor patterns with others. And we also, in this upcoming paper, have a step-by-step video guide and illustrated guide on how to build these sensors so that others can start giving their nows touch perception as well. We also need to work on adding wireless communication from the sensor to our algorithm and making it all happen in real time. So the last thing I want to talk about is our customizable emotion response system. So the robot is using its tactile perception system to identify what kind of touch is happening and where on the body, if it's a forceful or a gentle touch. And in order to be a good educational tool that the therapist can use with the child, the robot needs to respond in a way that makes sense for those touches. So we are looking at adding an internal emotional state for our robot, where it's inspired by the TAME methodology by Moshkina et al. And we're focusing in on adding moods to the robot. So not just a direct emotional response of, oh, you hit me, ow, or, oh, you pet me, I'm happy. Having a lasting mood that stays over time so that the child can learn about the long-term effects also of their touches on others. And so once this is added, once we have our emotion response system in place and our tactile perception system all built, then our robot will be ready to use in an initial user study with children with autism and a team of therapists. So I would just like to quickly show you a potential positive emotional response from Hera. You get to see it twice. And with that, I would like to thank all the people that have helped work on Hera. There are many people helping make it happen. And I would also like to thank you all for your very kind attention and ask you what comments or questions you might have.
Round of applause first. Yes, thank you, Rachel, for a nice presentation. Very impressive. Are there any questions? So I see a lot of clapping hands. Is there a rising hand? Yes, yes. Stefan, yes.
Rachel, thanks for your talk. I have many takeaways, very interesting. I was wondering about when you talked about the requirements and what is appropriate touch. So immediately I understood that you want to decode from the touch interaction let's say, some kind of appropriateness or how to react emotionally correspondingly. But I was wondering if the appropriateness is not encoded also, for instance, in making eye contact, or maybe some other cues like the context, or what you also mentioned, which was the mood, which is probably also encoded in a different modality. So are you considering this? What importance do you give it?
Yeah, thank you. That's a good question. I think, as you said, there are lots of different factors that go into appropriate or inappropriate behavior, including, for example, eye contact, or maybe the things that someone are saying to you. For example, if they say ow or no, that's different versus, this is fun or congratulations. Those are all different things. And I think we chose kind of to focus in on the touch interactions with Hera, mainly because we haven't really seen it being worked on right now. As you may have noticed, Hera doesn't really have a face that will react necessarily. It doesn't have like eyes that will blink or a mouth that will change. It's more like a stuffed animal. So we chose to kind of focus in on the touch aspects. But of course, when we do our initial study with children with autism and a therapist, my plan is to have the therapist there to also explain more what's happening in the interaction and guide the interaction. So the therapist might say like, oh, look, the robot, the robot's looking at you, the robot's waving, let's, wave, the robot wants a high five. It's not meant to be a standalone device. I think it's much better as a supplement or a tool for the therapist. So then the therapist can adapt the situation and maybe incorporate more of these other modalities, like you mentioned, that they already have the training for.
Yes. Okay. I think that's makes it clear to me that really it's going to be used by the therapist. So that's the designed use case. So yeah, he can use it as a tool for his sessions. Okay, thanks.
Yeah, of course. Thank you.
Are there any more questions? Okay, then maybe may I ask you a question or more?
Of course.
A few more? When you said koala, I initially actually thought that it would be an acronym, like saying it would be like saying that it would be some kind of robot. But then I saw that it's an actual koala robot, so it's very nice. Your robot or the koala robot really reminds me on the Sony IBO robot. I'm not sure if you know about it. It's discontinued product, but it has very similar characteristics. Like I think you can pet it, it will detect it somehow. I'm not sure if it has tactile sensors, but do you know? Did you compare your robot with the Sony IBO robot?
So I originally wanted to order an IBO robot back at the beginning of my research, but as you said, they were discontinued, so I couldn't get one. So I haven't compared them directly side by side. I know people have done research with IBO in the past. And I'm trying to think, I don't know, like you said, the tactile sensing it has. I know Paro, I don't know if you know Paro, the baby seal robot. It has some tactile sensing in certain discrete locations, like the flippers and the tail and the head, and you have to activate those spots, and it's based on a force sensor. So too forceful, it's sad. Less force, it's happy. And I think for IBO, it's also in certain locations. There's tactile sensing. I don't know if it's if what the tactile sensing mechanism is, but most of these robots that I've seen, they're only having touch sensing in very discrete locations. And if you don't touch that spot, then the robot doesn't recognize it. Or also if you don't, I used to have a toy robot dog, and it had a magnet in the bone. And if you gave it the toy bone, it needed that magnet sensor to react. So with these robots, you need to either touch them in the right spot or have exactly the right tool to activate them. And one of the things we're trying to do is do whole body tactile sensing, so that anywhere the child touches, the robot responds, because actually it can be quite frustrating if they touch and they do the right thing and the robot doesn't respond. It's not very fair to them. And if I can mention quickly for the koala, we chose it to be a koala because a koala is a non-familiar animal, is the terminology that the creators of Paro used. So with animals that you see all the time, with dogs or cats, it's very hard to make a convincing robot because people are so familiar with their behaviors. Whereas with a non-familiar animal, like a baby seal or a koala, you don't know very much about them, maybe just what you've seen on TV or read in a book. And so you kind of accept the robot's behavior as more natural because you don't have any other reference point.
Yeah, I think, I'm not sure who said it, but if something is really looks artificial, then it's fine. But as soon as it gets closer to the real object, if there's something missing, the people will find it looking weird. So that's a nice idea. And what I was wondering, did you already? I mean, right now you have only covered the arm, I think, and it's only early research. But did you show the robot to actual kids?
We have not showed it to kids yet. We just did, I forgot to mention, with the emotion response system, we're doing a video study right now, an online survey, and we had 51 participants look at our robot, look at its emotional response in different versions of the emotional response to find out what approach people thought was the most likable, most natural, most intelligent. Unfortunately, there were no kids in that study. We just did adults 18 and up. But hopefully some of that knowledge from the responses from the adults will transfer over to the children. You know, if everyone thinks it's frightening, maybe we'll redesign it. But if everyone thinks it's cute, then maybe we're okay.
Very cool, that's good. Next we have Christian? Yeah.
Yes. So thanks, Rachel, for an interesting talk. One thing I particularly like about whole body skins is thinking of human-robot teaming. So I always had this idea or this vision in my mind that you don't see the robot just as a machine or just as an autonomous system, but looking at your robot just as your body. So do you think this can also be realized with this technology? So do you think that, for example, when you execute a task together with a robot, that you get feedback from your robot, like touch feedback, so the robot is also touching you, is actually applying gestures to your body, and you do this vice versa, so like as in a reward, for example? And maybe a second question adding to that one, imagine that you have this system and it works. What do you think in terms of acceptance? Is this feasible? So will people accept this at some point, that it's really not a machine, not a robot, but you can really treat it maybe even as your friend?
Yeah, sure. So I will try to answer the first question first before I forget it. So you were kind of asking about, if I understand correctly, will we have the robot also conducting active touch, touching the user back?
Yes.
I think for this specific device, for Hera, the plan is only to have it conducting passive touch. So having the child touch the robot and the robot react to that versus the robot trying to touch the child. There's a lot that I'm sure you know goes into active touch, identifying where the person is, and also if the robot will need to model its own socially appropriate touch. So the robot needs to use its little arm to reach the right spot on the person. There'd be a lot more computer vision involved. So for this point, for this tool, it's just going to be a bit more reactive, and the therapist, I would foresee kind of creating the story that goes along with the child. So the child might maybe, gives it a hug and the therapist says, oh, that's great, good job. Or, oh, we need to be gentle. So the therapist kind of using it as a tool more than a totally independent little robot. And then for your second question, acceptance, whether people would accept this technology and use it and kind of treat it like a buddy. I think it is something that I could see the therapists implementing in their practice. The 11 therapists we talked to were very interested, and some of them volunteered, oh, send it over here, like we'll test it out for you. I think they're always looking for new technologies that can be implemented, and children with autism in particular tend to be very tech savvy, very good with iPads and technology is what we've seen. And so they might really enjoy interacting with a robot. One thing we'd like to see is the robot almost being like a safe training buddy, a practice buddy to practice safe interactions with and playing with. So that way the child can kind of build up their confidence for interacting with children at school, for example. But I do think a lot of testing will have to be done with these kinds of systems in the future to get to a point that the clinical community gives their full backing. That's just the nature of the clinical research.
All right, thank you.
Yeah. I think probably, Gita, correct me if I'm wrong, but
my audio was okay. Maybe the last question, there's only one question.
Yeah, sorry. Yeah.
Maybe from Van Ho.
Okay, thanks. Okay, so hi, this is Van, and I'm very enjoying your talk. It looks like looking at my research when I listen to your presentation, because the research question objectives exactly what we're looking for now, but we have a little bit different hardware for that. So I'm very interested in that. So maybe you can exchange more later. But this quick question is about the accommodation of the emotion. Okay, we're also working on that now, and we find it very difficult to quantify exactly that. So. Quick question is that, so how many emotion are you looking to discriminate in interaction with the children?
Yeah, thanks. And we can definitely correspond later in
Yeah.
trade topics, trade conversations.
Sure.
So the emotions that we're looking at right now, at this point, ideally, we are looking to do a continuous scale of emotions, from very positive to very negative.
Okay.
But our current work only is modeling it in one direction. We're doing it, we're looking at valence. So, which you're probably familiar with, but valence, yeah, being the mood, positive or negative. Ideally, we would like to also cover the second dimension of emotion, which is arousal or energy level. But we're not doing that yet, but that is something we're looking at doing in the future. So that's how we're modeling it right now.
Okay, nice. So I will follow you later by email.
Sounds good.
Thanks. Yeah.
Thank you.
Okay.
All right, then thank you, Rachel, for your presentation again, for contribution to the workshop. Then we will switch to the next presenter. I will introduce him shortly. So next we have, do you see my screen? Yes. So next we have Bakar Dawood. He is a PhD student at the Center of Advanced Robotics at Queen Mary, University of London, UK. He did his bachelor's in mechatronics engineering and master's in design and manufacturing engineering from National University of Science and Technology in Pakistan. And his research interests are soft robotics in general and specifically soft sensing. So I'm very curious about soft sensing, as I think it's a very challenging topic. I thank you, Abu, to being here today and showing us your ongoing research. I stop my screen sharing and the screen is yours.
Can you see the screen?
Yes, perfect.
Hi, I'm Bakar Dawood. I'm a PhD student at Queen Mary, and I'm working under the supervision of Professor Casper Althofer. And the topic I'm here, or the topic of my research, is multimodal skins for soft robots. Let's go through a bit of background first. Soft robots, as the name suggests, are made up of soft materials. They're compliant, and because of their compliance, they are very safe for human-robot interaction. That means they can be used in a close vicinity with human beings. And they are very economical to make as well, because, I mean, silicons are cheap, and there's not that much actuation system that's needed. It's just the compressed air. And now there are two main terms that you need to, that I would like to explain for the people who are not familiar with the area. Proprioception. It's actually the awareness of a robot of its position and movement. And then exteroception is its sensitivity or awareness to the external stimuli. Now, why is it a challenge? As Yutao mentioned that as well. As you can see in this robotic manipulator, there are 4 revolute joints and 1 prismatic joint. That means that it has 5 degrees of freedom. That means that by using 5 sensors, you can accurately estimate its position in 3D space. However, because of the compliance, a soft robot theoretically has infinite degrees of freedom. And that means we have to use infinite sensors to determine their position in 3D space. Now, these are different types of stimuli that a soft robot normally experiences. Figure A, it shows the external force being applied, and figure B, it shows stretch or extension, and figure C, it shows bending. Now, coming to multimodal sensing. The idea behind our research is that the sensors that are sensitive to force as well as stretch can be used to make skins, that are multimodal. For example, there are different sensing technologies, like some of the resistive sensors, they can respond to stretch as well as force, then optical sensors and the capacitive sensors as well. So if we talk about capacitive sensors, soft capacitive sensors, if they are arranged in an array, then that array, if stretched, there would be a global deformation. But if it's pressed at a certain point, that would be a local deformation. This equation here, it shows how a capacitive sensor responds to both of these things, stretch and force. As you can see, if you stretch a capacitive sensor, the area would increase, that you can see in the video as well. And the dielectric thickness, the distance between the plates, that would decrease as well. Both of these parameters would result in increase in capacitance. Similarly, if you press a soft capacitive sensor, the area would increase. There would be a bulge, a dome inside, and the area would increase, and the thickness between the plates, the distance between the plates, it would decrease. Now, coming to the capacitive E-skin that we have developed. So this skin is actually made up of 4 silicon layers. EcoFlex 50 was used for that. And the total thickness of the skin is 2 millimeters. We used carbon grease to make the terminals for the skin. Carbon grease is off the shelf. It's a product that's available in the market, and it's actually resistive. So you can just brush it by using a paintbrush to make any type of terminal that you want. So we used copper tape terminals to have a connection between carbon grease terminals and the external circuitry. And 3 layers of carbon grease terminals were made, and we'll move to the fabrication process for better understanding. This figure in A, you can see that there is just a 0.5 millimeter thick layer of EcoFlex. Then in figure B, we have brushed X terminals, and we put copper tape for external connections as well. And we have made another layer of EcoFlex cured on top of it. So these X terminals are enclosed between 2 layers of EcoFlex. Then the figure C, it shows that the Y terminals that are made, that are perpendicular to the X terminals, and the same process was repeated. And figure D, it shows the ground terminal. As you can see, the 4 corners have 4 terminals. So these are the connection of ground terminal to the external circuitry. And the ground terminal, it was actually the union of X and Y terminals. So the capacitance that we are measuring is between the X terminal and the ground, and Y terminal and the ground. This was the experimental setup that we used. And the figure A, it shows the flow chart. So we used a couple of 16:1 multiplexers to connect each terminal with the CAV424. CAV424, it's an IC, integrated circuit, that converts capacitance to a voltage, and the voltage can be measured through an ADC of an Arduino. Figure B, it shows the complete setup with the stepper motor as well for stretching the skin. And you can see that the skin is held in clamps, so it can be stretched. And then there was a bed underneath, so the force can be applied as well. Now, this decoupling algorithm, this is a work that's already been published, and we developed this algorithm to decouple force, its localization, and stretch from the parameters, from the values of capacitances that we were getting from the skin. As you can see that so the data that we were getting, it consisted of 2 × 10, meaning 10 X terminals and 10 Y terminals. So that matrix, first of all, its percentage change from the 0 state, it was determined. And then that 2 × 10 matrix, it was converted into 10 × 10 matrix. After converting it to 10 × 10 matrix, we found the peak value in that matrix. And after that, the localization, the coordinates of that peak were determined. And now here, it gets a bit interesting. because when a capacitive skin is touched, or any skin is touched, there is an effect on the neighboring nodes as well. To minimize that thing, what we did was we assumed 4 points along the nodes. We took those 4 points, and then we found the distance of those 4 points from the node of the indentation, or where the force was being applied. And then we use this condition that if the distance between those 4 terminals and the point of indentation is greater than 2, only those nodes would be considered, only those diagonal points would be considered. And we use those 2 diagonal points to calculate the stretch from the by taking their percentage from their 0 state, and then using the stretch calibration curve. So the algorithm, it behaved really good, although our data set was really small, but it gave us promising results. So this was the stretch that we calculated, that's plotted against the true stretch and the indentation. As you can see that when the stretch increases, the indentation, the force, same force, it has increased effect on the capacitance. And these are different plots that we made for after decoupling all these parameters, all these modalities. So you can see 5 millimeter indentation at stretch 1.124, 5 millimeter at 1.2475, and 10 millimeter indentation at stretch 1. Now, if our algorithm, it was behaving good, why do we need machine learning? The problem is that our algorithm, it finds the peak value in that whole matrix, and it ignores any other peak in that algorithm, in that matrix. So what if 2 forces are applied at the same time on the skin? That's why we collected a huge data set, and we moved to machine learning to solve that problem. And for that purpose, single force, we collected a large single force data set on all the nodes, and it was 18,000 samples. And our data, it actually consisted of 20 features, obviously X1 to the X10, Y1 to Y10, and then force, node number, and stretch. And for 2-point indentation, we used 2 forces, and there were 4 labels: force 1, node 1, force 2, node 2. So the model that we developed, it actually had 3 different algorithms in it. One was linear regressive, because we know, and it's mathematically evident as well, that stretch is linearly related to change in capacitance. Similarly, that's why we used linear regressive here, and then random forest classifier for classifying between X and Y, or the node number. And then the Gaussian process for force, because the force, it makes a saturating curve. Force and capacitance, it makes a saturating curve. So it increases linearly, but then it starts saturating. And these are the results that we got from our models. And this is actual stretch and predicted stretch, and you can see it behaved really good. But there is a bit of problem with the estimation of actual force that was being applied. And now this is the confusion matrix, and here you can see that the localization accuracy score, it was 0.88. And the problem here, that's also visible in the confusion matrix, that the neighboring nodes are also being affected. So the algorithm might behave a bit weirdly in that sense. As you can see, 76, and it's estimating 66 or something, right? So it's actually the neighboring node in the next row. So these were the results that we got from for two-point indentation or two forces applied at the same time. And you can see because so the data set, it was not that big for two-point indentation. It was 1,000, more than 1,000 samples, but it still behaved really good. And this is the confusion metrics for two-point indentation. And for two-point indentation, the accuracy score it's actually good because those nodes that we used for two-point indentation, they were quite far from each other. So we used 9 different points, and 0 being when force is not applied at any of the indentation, at any of the node. So 10 total 10 classes, and there was at least a distance of 3 terminals between the two forces. And our future work, it involves the application of this capacitive skin on a soft actuator. And we are also thinking about or working on applying the same multimodality principle on optical sensors and optical skins as well. If you have any questions.
All right, first, thank you, and a round of applause for you as well. And are there any questions?
Hi, Dawood. I have a question. Yes, I have a question.
Yeah.
Could you explain why you used the Gaussian process for the force prediction? Why did you opt for that technique in particular?
So Gaussian, because I mean, as I mentioned, that force and change in capacitance are non-linearly related to each other. And we have actually tried different algorithms, and including random forest regressor as well. But in our case, Gaussian process, it was actually producing pretty good results as compared to the other techniques.
So the saturation, I understand, makes it nonlinear. So you tried various nonlinear regressors like the random forest, and the GP seemed to work the best. Is that correct?
Yeah, yeah.
Of the ones you tried, obviously.
Yeah, obviously. Yes. Hello.
Well, I think we have lost him. The connection was not very good. Yeah. Well, I must say the confusion metrics looked to me really nice. Are there any further questions? No. Well, I might have one question for you.
Sure.
I mean, to me, it really looks really nice, the confusion matrix. It looks like you can really separate the touches yeah. And do you think the problem is solved by this, or do you think that you can still achieve better results, or what are further challenges?
Actually, as I mentioned before as well, in soft scans, when you apply a force at one node, let's say at one point, and when you are pressing it, there is a wavy, a wavy reaction from the skin as well. So I mean, that's not concentrated force. It actually affects its neighbors as well. Yeah. And so it's a bit difficult, to localize that force in a very good way. But yes, obviously, there can, I mean, different things can be used. That's why we are also exploring optical sensing now as well, to have a better, force localization technique.
But sometimes I think that the distribution of forces is even more interesting than the actual force values. So So how the forces are applied on the tactile sensor. I think Stefan made a lot of research in that regard by doing
Yes.
or applying imaging methods.
Yes. Yes.
Yeah, I think that depends on the use case. So if you want to do some recognition of objects, shapes, and so on, or the contact patterns, then the intensity maybe you can ignore. But if you're interested in the force value directly, yeah, you should interpret the data differently. Maybe I just really a quick question, and I think then we have to move on. I was wondering, what perspectives do you have for using finite element analysis for predicting the sensor behavior? Do you have any?
Actually, the first our first publication on this one, modeling of a soft sensor for exteroception and proprioception.
Oh yeah.
It's already published, and so I mean, we actually looked into it first. From that point of view, we used COMSOL, and being from a manufacturing background, I actually had a bit of experience in using COMSOL. So that was one of the first things I did, modeling of it, because we also needed a validation for this this idea that different technology, if one sensing technology, it behaves or it is sensitive to force and stretch, then it can be made into an e-skin to decouple different modalities. So yes, we did that, and it wasn't for the whole skin, the modeling part. It was just for one sensor. We studied it thoroughly.
Yeah, great. That's interesting. Yeah, I'm also working on trying to model or to integrate the signals of sensors with capacitive sensor with spatial resolution with finite element analysis to reconstruct forces, and yeah. So I very much interested in. So I will look up this work and yeah. But thanks.
Thank you. Thank you.
All right, then thank you, Abu, for your presentation and for your contribution. Then we will switch to the next two presenters. I will shortly introduce them. All right, so next we have Caleb Escobedo. He's a third-year PhD student at University of Colorado Boulder in computer science and member of the Human Interaction and Robotics group, HERO, advised by Alessandro Boncone. His research area includes physical human-robot interaction, collaboration, and robotic skins. And his research interests are control of safety in physical human-robot interaction, onboard sensors, multimodal perception for planning and control. And then we have Matthew Strong. He recently graduated in computer science from the University of Colorado Boulder and is starting at Microsoft this fall and preparing to apply to a PhD program for next year. His research area is physical human-robot interaction and collaboration as well. And his research interest is assistive robotics, onboard sensors, control of safety, and HRI, close proximity interaction. So we both have the same research interests. That's cool. And actually, those research interests cover the same interests as I have. So I'm very glad that both of you are here today, and they will show their research in ongoing proximity or beyond proximity sensing towards the actual use of the sensors, I think, in applications. So the screen is yours. I will stop this.
Okay, thank you, Ito. Okay, so I'm Caleb Escobedo, and I'll be presenting this today with my colleague Matt Strong. And today we're going to be talking primarily about contact anticipation for physical human-robot interaction with some onboard sensors that we've developed in our lab, the HERO lab at University of Colorado Boulder. Okay, so let's get started with our motivation. So our motivation here is close proximity human-robot interaction as humans work together to complete complex tasks, and they often make contact. So we just have a couple of scenarios here where humans make contact and there's kind of a cluttered environment that we would eventually like to have robots in. So some assistive behavior, like holding objects or handing over tools, or also collaborative behavior where robots and humans are working on the same goal, and they would hopefully be working in a similar space when they're completing these goals, like sorting things or doing something on an assembly line. And so in order to accomplish this, we first thought about our perception modalities. And so with some motivation by Stefan Navarro, one of the co-organizers here, we decided to not use external depth sensors because we've heard that they are prone to occlusion when you're getting close to a robot and actually want to interact with it. And that onboard depth sensors or onboard proximity sensors in particular can offer this close proximity interaction and not lead to occlusion when you're interacting with the robot. And so we chose to take this path. But in addition, we're also interested in just robotic onboard sensing in general, not just limited to proximity sensing. So for this, we developed a custom sensor unit with a collaborator here at University of Colorado Boulder named Marietta West. And on our sensor units, we have a proximity sensor. We have an IMU for automated pose calibration. This is also a paper that was accepted to IROS 2021 for automated pose calibration of these sensors on robotic manipulators. So please check that out or reach out to me if you have any questions about that. And then we also have a wireless communication and battery power with a Wi-Fi chip. So we wanted this to be self-contained and you'll be able to plug this in and just get data kind of really quickly over Wi-Fi and not have to worry about wiring and putting it on the robot. And then lastly, it's pretty small. I have the sensor here for you all to see. So this is the battery and the sensor itself, just so you can get an idea of the scale. And lastly, it cost $36 for the parts, and we manufactured it ourselves in-house. Okay, so now I'm going to pass it on to Matt to talk about our research goals and what we're doing with these sensors.
So given the current motivations of our work, we have three main research goals. The first one is to anticipate meaningful contact, that is, the human wants to make contact with the robot, and to have this reduce the actual force made with the robot manipulator during physical interaction. So if you look on the two figures on the right, the big figure shows my hand getting close to a robot. And if you look at the bottom right picture, it shows two proximity sensors on the robot detecting both my hand and part of my arm. And we can leverage this information in order to anticipate the contact, which is shown in the red area. Secondly, we want to avoid unwanted collisions. That is, if the human is just trying to do their own task and they don't want to actually meaningfully contact the robot, then the robot should be aware of that and move out of the way as necessary. And finally, we want to resume manipulator trajectory once contact has been made or once the robot has voided the human. And one of the reasons for this was to avoid error states, because something we noticed is if we didn't have this smooth transition out of contact or avoidance, the robot would tend to enter error states that would just end its operation, and you couldn't really do anything after that. So with this in mind, we propose to group all of these into a single unified framework.
Okay, so now I'm going to go over our framework. So I know this looks like a lot to start with, but I just want you all to focus on this top part, the section headers. So we view this as kind of having four steps in our system. So first is object detection, then prior to contact behavior, what we're going to do before we come in contact with the object, then contact detection, which is our main contribution in this work. And then lastly, we have some post-contact behavior. So once we've noticed this contact, what do you want to do with the robot? And we're just going to focus on this first one right now. So this obstacle detection. So first, we want to talk about how we're moving the robot here. We have an end effector velocity that we're controlling, and this is taken from Itao Ding's work, one of the organizers here as well, where we have our main task error, where we're controlling where the desired velocity of the robot. We also add this another term to avoid singularities, as Itao Ding presented. And then we add an additional third term here to drive the robot to its middle joint limits when possible. And this is because we found that if the robot's trying to avoid an obstacle too much and doesn't kind of driving back towards these middle joint limits or some area where it can leverage its redundant degrees of freedom, then it's very hard to recover, or the robot makes these jerky movements. So what we do is we take this and through Ding's work again, we transform this into a quadratic programming notation. So that way we can put some restrictions on this and also adapt to obstacles in the environment. So just first, we're adding these joint velocity limits on these upper and lower bounds of our joint velocities. And then secondly, we're adding these movement restrictions on the robots. We're dynamically determining control points along the robot closest to an obstacle. And then we're saying that we're restricting the velocity or adding a little bit of repulsion there to move away from it. Okay, so with this in mind, we can take this equation here, and we've sensed the obstacle and we're moving it around, and then that brings us to our second kind of bin here, which is prior to contact behavior. And notice that in this prior to contact behavior, we have two different forms. We have one that's obstacle avoidance and another one that's end effector velocity scaling. And this is because we found that if we didn't scale the end effector velocity, it felt very unnatural trying to approach the robot because it seemed like it was trying to avoid you at all costs and like jerking around and having a little bit of jerky motion. So now we're going to show you what this obstacle avoidance combined with end effector velocity looks like. So this is me placing my hands up to two sensors, and you can see the robot turning as well as slowing down. So we have both the avoidance and scaling, and these are both terms that you can change the weights on. You could make it slow down or repulse more or try to avoid more, depending on your application. I'm going to show you all the video one more time, just so you can see the proximity readings on the right side. So these are the live readings in RViz. As I put my hands up, you can see those proximity sensor readings, and the robot reacts to that behavior in real time. Okay. And now I'm going to pass it, or we have one more. So I'm showing the results for this. The robot is always in these experiments moving in a circular trajectory. And so you can see that as we sense an object, the robot veers from its trajectory, but then over time, it ends up recovering from that trajectory and ends up going on the nominal circle that we would like it to go on. So now I'll pass it on to Matt Strong, and he'll talk about our external force calculation.
So once the obstacle overcomes avoidance, that is, the human wants to make contact with the robot, we need a way to detect if contact has been made, and if it has been made, the magnitude and direction of that force. And so this kind of revolves around mean external force calculation, in which we can operate on noisy external force data and compute the external force of like a human or an object. And so our main contribution is dynamic contact thresholding. And so here we basically have contact thresholds that determine if contact has been made. And these dynamically change over time based on information about the force data, but also information about what the proximity sensors have sensed in the robot's nearby space. So the two terms we have here are TU and TL. TU is the upper positive threshold. TL is the lower threshold. That's the negative threshold. And so both of these terms are first computed as the mean external force over like a sliding window. Then we have a base contact force, which determines this many newtons above or below the mean should count as contact. Like 5 newtons kind of below this mean, that's contact. And the next component after that is a force based on standard deviation. And from our experiments, we observed that as the robot does move faster, the force data is much more noisy. And as a result, it has a higher standard deviation. And because of that, when the robot has this more noisy force data, we want to grow the bounds of the thresholds because we are more uncertain if contact is made. And our final, and I would say most important term, is the obstacle proximity term. And you might note that the sign of this is different than all the additions we have in the upper threshold, for example, and it's a plus sign in the lower threshold. And let me kind of motivate this with an example. So if I have the robot here and an object in the negative y direction of the robot, if this object in the negative y direction makes contact with the robot, that's actually a force in the positive y direction. And so that's why we have to kind of have that reversal of signs here to kind of prepare for the contact in this direction, even though the robot's on the negative side. So altogether, this allows us to be more sensitive in that direction to contact. And so after this, contact has been made and the contact threshold has been exceeded, we want to apply some kind of reactive behavior. And while in our case, the robot simply moves away in the opposite direction of the force, this reactive behavior can be anything. It could be maybe switching modes or switching controllers, anything that the researcher or developer desires. So this ongoing videos that you're seeing here is our robot doing experiments with a single sensor activation. So in the upper right, you can see the RViz proximity readings. You can see Caleb getting closer right there. And on the graph below that, we have the external force and contact thresholds. So the green is the force data, and the two blue lines like that span it are the thresholds. And when we play that again, you can see as Caleb gets closer, the threshold does dip. And at its lowest point is when contact is made, and the contact kind of punctures the upper threshold. And that's what we want. And the last main thing I want to point out is that as Caleb does approach the robot actually does kind of start to tilt as Caleb gets closer. So as you can see, it does tilt, and that's actually the avoidance behavior and the end effector velocity scaling behavior coming in. But because Caleb is committed to making contact, he's able to make a very smooth and natural contact.
Okay, so additionally, we wanted to show that we can activate multiple sensors on the robot end effector and have contact in different directions other than the Y direction. So here, activate all the sensors on the robot end effector, and then I push it back in the Z direction. And here, what we want you all to notice is that in our graph, we have a reduction in the positive Y and negative Y directions thresholds, but because I'm pushing it back in the X direction, we don't see that spike in contact force that we saw previously. And I just have this light force because we've reduced the threshold in the X direction. Just going to show it one more time. Yeah. And so that brings us to our results that Matt will show you.
So yeah, going back to our main goals, our first goal was to have reduced contact force. And as you can see from the graph on the right, without proximity, the external contact force is nearly 2 times that of just having proximity sensors to anticipate contact. And both the second and final points can be kind of summed up together in this graph that Caleb showed earlier, where as the object gets close, the robot is able to deviate from its main trajectory and avoid contact. You can see it pretty quickly gets back on its main trajectory and it's back to normal. So we were able to achieve all 3 goals.
Yes. And then 1 second, I think one of the slides is hidden. Okay. And then we wanted to introduce some future work on what we're working on. So we're working on more sensor development for easy, this term plug and play, is we really want sensors that anybody can use, just kind of plug in like I have here with the battery and get data so they can experiment on quickly instead of having to develop these. So we're working on this automatic message communication, and then we're also very interested in any collaboration. So I know a lot of people here are working on proximity sensor technology or skin technology, so please reach out. In addition to this, we're also working on new sensor prototypes. So this is one of the sensors, our prototype sensors that we've developed in our lab, and it has much more sensing capabilities. It's on a flexible PCB, and we're trying to have more dense coverage of these sensors eventually. So we're iterating on this design to have more density of proximity sensors with still this easy plug and play. You can choose a battery or a wired connection when you're doing this kind of experimentations on what sensors you want on your robot. And lastly, we'd like to say thank you to the workshop organizers, Itao Ding and Stefan Navarro, for their work, because it has been very inspirational to us and really helped us as we're moving along here. And now we would like to open the floor to any questions that you all have.
Yeah, thank you guys. Thank you a lot for the nice mention. And I think your results are really great. So it's a nice feeling to see that the contributions can be useful for the community. So thanks again. And yeah, as you said, if there's any questions.
Well, if no one wants to ask something, I definitely have some questions from you, for you. First of all, are you considering the velocity of the obstacle in detecting potential impacts or the potential impact?
Yeah, currently we're not estimating the obstacle velocity as we approach it. So we were thinking about that for something that's coming fast. And if you could have some kind of behavior to quickly move away, you could reduce the contact force as well. But we just haven't explored that yet. But definitely something on our minds is to reduce like those hard contacts.
Yeah, I definitely think that you're on the right path. And also, I'm not sure if Shinichi Hirai is still here, Professor Hirai. He has shown us his flexible capacitive proximity sensors, which I found interesting. And he had also the same idea of some kind of reducing impact forces with his sensors, but he was more into soft robotics. And maybe there could be something that when something reaches out to the robot, that the surface of the robot can become softer, for example, by inflating some kind of bags or balloons. Or
yeah,
airbags.
That is definitely something we've collaborated with a material science group here on having like inflatable or embedding this in some kind of EcoFlex material. So that way it's a kind of a softer, more skin-like. And yeah, definitely something we want to also work at. So I'll reach out to that professor.
I had a small, sorry.
Yeah.
Yeah, I just wanted to shortly ask about, so I think you mentioned the possibility that how to distinguish between desired and undesired contact, and that, so one of the cues you found interesting was the reduction of speed. So that basically the robot should slow down as to, check whether the incoming contact will be desired or he should continue avoidance motion. So yeah, I just wanted to know if you, what kind of ideas you have for this. So you think this will work nicely, or?
So for that, I think we were really trying to think about what do we want when we are coming to like just touch a robot or grab a robot, because I think most people, their first instinct is that they want to interact with it or do some kind of gravity compensation mode when they see a robot. And when we tried to reach towards it in any other kind of with any other kind of controller, when we didn't reduce the velocity, it really felt a lot like really jerky, and it kind of scared us. So that was just from our personal experience of the robot that this ended up feeling more natural, that it slowed down. We also think that eventually it could be a good study to do, that the robot is recognizing that you're in the environment by slowing down. So it's acknowledging your existence, and that could have some social implications, that I think the robot is smarter than it was otherwise because it can perceive me, it knows I'm there, it's going to be more careful around me.
Yeah, the jerky motion was also something that I experienced. So because I think there should be some kind of switching over from a pre-planned trajectory and then switch over to the reactive motion task, so that the jerky motion is a little bit compensated by that.
Yeah, another thing we're thinking about in these scenarios is how important is it to continue upon the task. So we've seen a lot of work like Fabrizio Flacco's work that was really inspiring to us on this repulsive forces. And we were wondering how much in these scenarios should the robot really continue its task, because if it's trying to reach around you all the time, that's kind of unreasonable for you to expect that kind of motion. And so we're thinking at some point you should just stop moving towards that and do something else. Yeah.
And we have one question from Professor Van Ho.
Hello. Sorry, I missed the first part of your talk. So I have some questions. So how many sensors do you need for one typical robot arm? And with the limited sensors, is there any blind spots regarding to the proximity sensing? And how do you specify the contact locations and the likes?
Okay, so on our robot, I believe we just had 7 of our proximity sensors, but we're really only leveraging the first 3, or no, first 4 on the robot end effector. But to address this, so we're going towards more dense coverage in our sensor development in general. So we want to be able to kind of have it modular so I can plug in another proximity sensor if I want to. And this goes to some other work that we mentioned that we published in IROS 2021 to automatically calibrate the location of these sensors. So we can place them anywhere on the robot end effector, and then we'll locate the pose. So that way we can locate the obstacles after that. And that was one of the things we really wanted to do, is kind of make it general for the placement. And then secondly, we in this workshop, actually, we have another workshop. We have a workshop submission that's about fusing visual and proximity data to create a more holistic view of the robot's environment. And so in this, we're kind of moving towards that. We don't think that just sensors in the robot will be the entire solution, but that it's going to be a fusion of multiple sensor inputs and then trying to mitigate the contact. We also think about this in humans, that accidental contact happens very frequently, and what is kind of the level of contact avoidance, or like level of contact that we're okay with making, especially in these cobot scenarios.
Yeah, I totally agree. And looking forward to the paper at IROS 2021. Yeah.
Thank you.
All right. Yeah, just to add, maybe adding a few LEDs on your sensors might be good, because the TU Munich team, they detect the sensors, or the position of the sensors on the robot with vision, by turning on the LEDs and all.
Okay, very cool.
Yeah. And also using, I think, the accelerometer data.
Oh yeah. Oh, another thing is that we have an accelerometer, or an IMU on the robot,
Yeah,
and
cool.
what we've something we've seen with that is there have been other papers that are trying to notice when the contact force has been made with these external or onboard IMUs. So they have other kind of applications as well, other than calibration.
I think that's very similar to Catherine's work here. She was a speaker this morning.
Okay.
And all right. When there are no further questions, yeah, I hope to see more from you guys, even and even more when you have more sensors. We only have
Okay, yeah,
limited
thank
by
you so
sensors, I
much.
think.
Yeah, definitely.
And yeah, to conclude everything, I think it was a nice PhD forum this time. A lot of participants this time, and also thank you for all the audience for tuning in. And if you want to contribute to this workshop in the future, or want to help us out, just contact us. You can participate in the team. And with that, I would thank you for coming today, and we will have our next session now. And thank you very much, and see you.
Yeah, thanks a lot,
Thank you
guys.
very much.
Thanks, everybody.
Take care.
Bye.